So this is the outline of my topic. So first of all, I would talk a little bit in general about nanotechnologies for photovoltaic. And then there's one big part of nanotechnologies is nano-photonics for light management, and a little bit on metal nano-networks for transparent electrodes, and some nano-patterning works for local contacts. So basically the three areas that these are the ones that I worked in terms of application of nanotechnologies on photovoltaics. So what is nanotechnology? So is it smaller the better? So probably one of the most important events in the history of nanotechnology is that a talk given by Richard Feynman at Caltech in 1959. He predicts a lot of the name of the talk is "There is plenty of room at the bottom." So he predicts a lot of new things and how the technology, how the future of human would go. He thinks, obviously, as a physicist, you always research on something big and bigger, bigger and bigger, and smaller and smaller and smaller and smaller. And he thinks getting smaller and smaller is the future of research. So mainly because we don't understand what happened at small scales. So for curiosity, we research on that. There are three major problems we have at the small scales. First, it's very hard to characterize, to know exactly what happened at small scales, because we have to detect, we have to characterize, before we know anything, we need to know exactly what happened, and it pushed the limit to all the detection techniques. And even we say, okay, we don't want to detect what's happening, we just want to use some first principles to understand what's happening in a small scale, but also you have the problem, it's very hard to calculate. For such small scale, you always require very high computing power intensity in order to make any reasonable simulation that can reflect the microscope world we are living in. And also it's hard to understand because it's so much smaller than the world we live in every day, so it's not intuitive. There are a lot of things that according to our, it's actually opposite to our experience, so it's quite hard to understand. But because we have so much stuff that we don't understand, we think there is a lot of chances for a leap. It's not like incremental work. If you find something fundamentally new, you may just change a lot of things completely. So that's a big chance. It's so powerful, but it's so complex. So we all understand, I guess we all generally agree, optimization happens when we are able to manipulate individual atoms. So we should all agree that, right? So all the macroscopic effect is actually accumulating of the behavior of individual atoms. So if we can control that as we wish, and we can always get what we predicted, and what we can maximize for solar cell, for example, efficiency and performance. But if we go down from microscale to nanoscale, it's actually 10 to 3 times finer if we talk about 1 dimension, and 10 to 6 times finer 2 dimension, 10 to 9 times finer in 3 dimension. The degrees of complexity is just increased dramatically. So even if we have very fancy things happen at the nanoscale, it's very hard to sort of build something that, for example, like solar cell with full size wafer or something like that. It's very difficult. So we have to look at some advanced nano fabrication technologies, which means they have to be simple and also accurate as much as possible. So nano is just everywhere, no matter you realize or not. You may think it's a very fancy thing, but it's just happened every day. First of all, almost all the deposition processes start from nanostructures. So this is a picture showing the plating. So in the beginning of a metal plating, you always have the nano metal islands, and the metal islands grow up to thin film. So the nano structure is just there, and we know all the crystals are just repeating structures of nanoscale units. So why nano for solar cells? That's another question. So I like this watermelon analogy, which help you to think. Doesn't work properly anyway. Help you to think the working principle of solar cells. So obviously, you want to have high performance. That means you want to increase the JSC and VOC and fill factor. It's like you want to increase the height of the watermelon, and you want to increase the diameter of the water pipe, and you want to minimize the leakage as much as you can. It's representing resistive loss and recombination loss, whatever. So by introducing nano-photonics, you can have big increase in JSC, and the nano-electronics, you can probably get high fill factor because you just reduce the resistive loss. And with some advanced quantum dot band gap engineering, for example, you can expect high VOC. So that's one aspect, is to try to increase the performance. On the other hand, you want to enable some solar cell fabrication that couldn't happen at larger scales. At nanoscale, you may have different material features, like you have the melting point may change, viscosity may change, conductivity may change. So one of the probably well-established technology that, if not commercialized, is going to be commercialized is the DuPont's InnovaLight technology, silicon ink. So what they do is they have doped silicon in the ink, and they want to have the ink applied on the undoped or lightly doped solar cell to make a local high doping area. But if you think about the normal silicon material, like a bulk, it has melting point at 1400. So it's quite limit the process of applying that on a lightly doped silicon. But if the silicon nanoparticles is in the nanoscale, because the surface always have activation energy lower than the bulk, because it's very easy for the atoms to go out. So, but at nanoscale, you have very high specific surface area. That means your surface area to volume is very high. So the melting point of the material actually degrade dramatically. In this case, it can be below 500 degrees, which enable a lot of solar cell processing. Then I will talk a little bit about nano-photonics light management. So what is nano-photonics? The common definition is you either have incident light that is confined in a nanoscale, or you have a homogeneous illuminated light illuminating on a material in a nanoscale. Because it's basically the photonics research is the interaction between the light and the matter. So one of the thing, once it's followed to nanoscale, then you can consider it as a nano-photonics region. So what's the unique feature in this nanoscale is when the feature size of the materials are smaller than the wavelengths of light, you cannot actually consider it as a ray. So we have very well established knowledge on classic ray tracing models and refractive index models. They may not work at nanoscale. So rather than using these models, people have to use some kind of more basic first principle technologies to check, to simulate or check what's happening. So you have to consider light as electromagnetic wave. So one of the popular the method used to finite difference time domain method called FDTD method to solve the Maxwell equations in partial differential form at local grids. So you really look at what's happening exactly at the nanoscale, and you just add more and more, let it repeating, and you can see what's happening at a larger scale. So that's one typical method of investigation. And for some cases, classical electrodynamics is, in most cases, is enough. But for some cases, quantum mechanics is needed when the light is confined in semiconductors. That means it's similar to semiconductor band gap. You have optical band gap, you have photonic crystal, and for these kind of things, you have to use quantum mechanics language. So, and I will talk about popular nano-photonics technologies for PV, which are Plasmonics, photonic crystals, and one thing I find is very interesting is whispering gallery mode technique. So what is Plasmonics? How it works? So I like this water polo analogy, which is inspired by Cashapol's balloon analogy. So if you don't quite understand what's happening on the right side, you just need to think about what's happening on the left side. So first of all, you throw a ball in the water. So it's similar to you have a light strike on the metal nanoparticles. And the ball starts to move up and down. And on our right-hand side, the electrons in the nanoparticles actually oscillate collectively because of the polarity of the E field of the light. So when the light propagates downwards and the polarity changes, and also the electrons move from left and right and right from left because of the change of polarity of the incident light. And on the left-hand side, and the energy will propagate as wave in the water. So in the dimple waves go around the ball. And on the right-hand side, the oscillation will, it's like a radio. You will radiate electromagnetic wave to the surrounding environment. So and also on the left-hand side, you actually won't, the energy will not go much to the air because the density of the air is just it's too small compared to the water. So most of the energy will go to the high density material, which is water in its case. And on the right-hand side is a high refractive index material, which is a substrate. So you have significant forward scattering effect on the right-hand side, which when we make solar cell, we like that because we call it anti-reflection effect. And on the left-hand side, you say, okay, we have wave and energy just escaped. What are we going to do? So why don't we just build a wave power plant and connect all the energy, just surround it? So on the right-hand side, why don't you just put a solar cell underneath so you can receive all the light? So once you understand the water polo and you understand the working principle of plasmonics. So why plasmonics are so attractive for photovoltaics? So if we always think back the water polo thing, and you know that you have anti-reflection effect because the energy always goes to the high refractive index material, which is the silicon for our research. And it has scattering effect because when the nanoparticles re-radiate, the electrons re-radiate the energy, it won't go straight underneath. It will go everywhere. So that's kind of a scattering effect. That's what we like because we improve the patterns of the light. So, and one thing special is we may make use of the near field concentration effect, which means we have the energy in the trap mode. To understand that, if you go back to this page, you see even if the light shining on this nanoparticle, the ones adjacent to them will also have the corresponding move because of the internal field in this nanoparticle. So if this is negative, then this one will probably be positive. So it's actually not only working on the particle that light striking on, the energy will also propagate in this direction. So instead of let the energy go downwards, it can go sideward. That's a trap mode. So why this is attractive? Because for example, very long wavelength lights, you can just trap the light down there until it's absorbed. So in principle. Otherwise, you have to let it bounce back and forth maybe 4 square times and see what's happening. And actually, UNSW is the pioneer for plasmonic research. And I think we first experimentally demonstrated light trapping benefit from the plasmonics. Yep. So I will talk a little bit about my research experience on plasmonics, which I spent, I think, 2 or 3 years on that. And there are a lot of things to consider. I think it's a very good practice actually for a PhD student because most of the work I present here in this part is done within my PhD. So the first thing we need to think about is what metal material are you going to use? The different materials have very different properties. So if you look at the reflectance curve and the nanoparticle parasitic absorption curve, they are very different. Now we're comparing silver, gold, and aluminum nanoparticles with the same diameter. So they are different because they absorb the light at different level. And they have different sort of interference with the incident light. For most of the particles, actually, you see you have significant absorption here. That's because basically the oscillation in the particles just become heat. And for the other part, you also have a little bit reflectance. That's because there is a destructive interference between the incident light and scattered light. That's what we call Fano effect. So you see all the particles, materials behave differently. Before we started this work, we thought actually in the literature, gold and silver were the standard plasmonic materials until we find aluminum is way better than them. They have less absorption, less reflectance. So if you look at the red one is the aluminum one. So, but the problem is all aluminum suffers from fabrication difficulties because it's so easy to oxidize. So no matter you use physical way, you deposit and you anneal, or you use chemical way, you just chemically synthesize it, it's always difficult. So it's quite challenging. But fundamentally, that's better than the rest. And also, yeah, so let's jump to another page. So we know what material we use, and we see the fabrication method. So basically, there are 2 methods I just talked about: a physical way, deposition and annealing, and the other way is chemical synthesis. So there are a few things you need to consider in terms of choosing what kind of method you use to fabricate these nanoparticles. First is the control fineness. I personally think the physical way is the simplest way. But the problem is you are very much limited by the control method. You can control the temperature and you control the thickness of the thin film you deposit, and you just anneal and you see what's happening. So you don't have a lot of freedom to control the nanoparticles. But for chemical synthesis, you have so many parameters to play with. You can make nanoparticles, nanospheres, nanorods, nanowires, nanocubics. You can have a lot of things. Then use chemical way, you actually you first decide what shape you want, and you see if you can find a way to synthesize it. And the fabrication cost is another consideration, but I won't go too far on that. And some interestingly is as I said, you need to think about what shape of material you use. So one interesting example is, usually what you fabricate from the physical way is you have hemisphere particles, which means the contact area between the silicon and nanoparticle would be flat, and you have a bond. And for chemical way, you can have a very nicely shaped spheres. So if you look at the plot underneath, you will find the sphere actually give you overall better scattering effect. But so this is a energy surrounding the nanoparticles. But for hemisphere, you actually have less electric field around it, but you have much more forward scattering. So it really depends on how you design it. For example, in this case, hemisphere may be much more preferable for front side coating because you have better anti-reflection effect. But for the nanoparticles, which is spherically shaped, and you probably put it on the back because the scattering to large angles is more important than forward or backward scattering, because you can easily put another backsurface reflector behind the nanoparticles and reflect whatever transmitted back to the solar cell. So it's just some considerations. So material limit, I just talked about that. Aluminum is very good, but its oxidization rate is very high. And also if you look at this curve, the underneath one, you will find absorption, although of aluminum is better below 600, but actually absorption is higher at the long wavelengths. So probably aluminum is not a proper material for the BSR application. So then you want to put it on the rear side, if you want to put it on the front side or embedded inside. So that depends on your cell design. But usually embedded configuration is I never heard anyone get any efficiency or performance improvement on that. Simply you put the metal in a bulk material. That sounds terrible. And this is the figure on the upper right hand side is the comparison between the front located nanoparticles and the rear located one, and the reference is the black curves, and you see the both have enhancement, but for the front located one, actually we look at the lower curves. At the 300 to 400 nanometers, you have a dip. That dip can kill the performance if you put it on the front side. But if you on the rear side, you don't have that problem because of short wavelength light. We just cannot go through. So that's good. Thanks. Yep. And then dielectric environment. So what kind of, you use titanium dioxide, silicon oxide, or you put it on a silicon, or you put it on silicon nitride. You can play around with the environment and the particle size. So I won't talk too much about that, but you see this is one solar cell, and actually one mini module with 9 cells. And if you have different silver nanoparticle size and different thickness of nitride, you can have completely different color on the surface. That means the resonance of the light that is scattered is very, very different. So you can have a lot of parameters to play with until you find the optimized one. So then is Plasmonics itself may not satisfy you, and you may consider to add it on top of other light trapping things. So how about hybrid structure? And we demonstrated very significant improvement when we put on the nanoparticles on our solar cell. The first one is the thin film cell that I made during my PhD. So this is the nanoparticles put it on the rear side with a back-surface reflective paint. So what we get is this curve, the very high EQE boost, up to 44%. And this was the benchmark before we have the plasmonic work. So that conventionally, this white paint, which is this black curve, that was the benchmark of thin film solar cells for maybe 5 to 10 years. So we really boost quite a lot due to this technology. And as we can imagine, it's very difficult to get enhancement light trapping effect on single crystalline solar cells. But for multi-crystalline silicon wafer solar cell, we still have some space to go. So it's very interesting. So if you look at, it's not very clear. The blue one is the one with nanoparticle and on top of the silicon nitride. And the green one is without nanoparticles. You actually have a decrease at the peak where you have the where you optimize the wavelength for your thickness of silicon nitride. So because with silicon nitride on top, you expect almost 100% transmittance. So somehow, as you can expect it, the break the ring, so the scattered and probably the path length change, so you won't have the ideal cancellation anti-reflection effect. But at the short and the long wavelengths, you really sort of get benefit from the nanoparticles. So you have a little bit trade-off, but you boost on the short and long wavelengths. So for this particular solar cell, we have not much, but good enhancement from 35 to 35.5 milliamp per square centimeter. And this result actually matched very well with one of our earlier publications where we simulate the result, also show the same decrease at the medium wavelengths and boost at the short and long. So this sort of experiment confirmed by the theory, or the other way around. So the last thing I will talk about the plasmonics is possible near field enhancement. So it's quite. So what you can see is this is silicon and the silicon nitride and the nanoparticles. When you move the silicon and the nanoparticles, silver nanoparticles, closer to the substrate, silicon substrate, you can see actually the boost of the near field at the surface. So we think that might be a good thing. So we did a series of experiments, put the nanoparticles embedded on different positions of the silicon nitride. And what we find is that as we move further away from silicon, we get lower JSA enhancement. And this curve is is fitted with the exponential function. And we know the near field decay is exponential function. So this is sort of indirect proof of the near field enhancement. But obviously further study is needed, because at the near field, the silicon had to compete with the nanoparticle in terms of absorption. So the parasitic absorption of nanoparticle is very strong, and silicon, because it's indirect bandgap material, and you think it might not be very good. So the more details of the competition needs to be started before we have solid conclusion. So then, finish of the plasmonics and other thing about the nano-photonics design, and you can have photonic crystals, which you use quantum confinement to control the propagation of the light. So it's like you introduce band gap for your semiconductor material, for your electron band gap. This is optical band gap. That means at some point the light is not allowed it to move to one direction, one angle. So if you have a look at this, you actually find a very large boost at some point of the spectrum, actually higher than 4n squared predicted. Yeah, but sacrifice of other wavelengths. It's always like this. So if you attended Martin Green's one of the tutorial talk, he talked about the trade-off between the if it is possible to go over 4n squared. The conclusion was not at the broadband condition. You may have a little bit boost at some wavelengths, but you sacrifice other regions. And this is photonic crystal, and the whispering gallery mode is something interesting. This is sample cathedral and Tiantan of China. So it's very interesting if one person sort of talk very whispering here, and you can hear from the other side. That's actually, it's a sort of a propagation of sound wave to actually form a kind of lossless mode. So people, smart guys, have this idea, and they think, oh, why don't we use this mode on solar cells? So they develop this kind of resonant spheres. So the light, once it gets in, will bounce back and inside and will not escape. Only if you at the point where it is adjacent to the absorbing layer. So it's like an integration sphere you use for your transmittance, reflectance measurement of your sample. So it's actually, you can consider it as a detector underneath. So it actually, every time it goes down, it will absorb a little bit. Every time it goes down, absorb a little bit, because if you make the spheres very little absorbing, and you can actually have very high absorption to the absorber layer you want. But the problem is, again, you only boost at the particular wavelength. And then another bunch of smart guys, they think, oh, we can lower down the quality factor, so we can introduce second order or third order, fourth order modes, let them bound inside. And instead of using sort of anti-reflection coating on top, why don't we just make the absorber layer like this? So this is actually PIN structure. They make nanocrystal silicon thin film material like this. This is the active layer. So the sphere itself is the absorber layer. So they can sort of have multiple coupling of the light at different frequencies, and they claim they have very high absorption. They don't have any electrical characterization results, but optically it looks very good. And it's the absorption is much higher than the thickness itself. What I mean is, if you fill it up with silicon, you actually have less light absorption than this empty hollow structure. So this is something interesting. So talk about some chances and challenges. So first of all, broadband is the biggest challenge from what I understand for nano-photonics. Because at the nanoscale, you actually, the light cannot actually see the material. It only can interact with the material when it sort of react with it at some mode. So for most of the nano-photonic design, you won't have broadband enhancement. And this is really what you want. But I think if you, one exception is if you can add on sort of down conversion and photonic crystal, and you can down convert the short wavelength light to sort of to long wavelengths, and design a structure that's just lying on there. So you know exactly what you want to boost, and if that the wavelength range is the range you want to boost, you can actually design a structure like this and achieve very high absorption. And obviously homogeneous enhancement of the entire wavelength. How many channels can you put on a surface? One interesting thing is, okay, you want to have multiple channels, you want to have a broadband absorption. Why don't we just throw different nanoparticles with different sizes and see what's happening? But the problem is one nanoparticle physically occupy a space. So if you have at this location, you have a boost for 900 nanometers. Actually, you lose ability to boost 600 nanometers. So if you integrate all together, you actually won't get any broadband enhancement peak like this. So, and obviously you want to have easy integration to solar cell and low cost, easy fabrication and scalability. So like 2 years ago, I did a simple calculation for if you claim you have a very good technology, you can boost the efficiency by 1% absolute, then you need to cut down the cost way below $10 per square meters. So that's very challenging for most of the nanotechnologies I'm talking about and I'm not talking about here. But this is a very key factor, but it's not fundamental. So you just keep this in mind, oh, I have this fancy idea, fundamentally it works. And in the future, if someone develop a cheap technology and you may just adopt in. So that's, and then obviously you want more smart ideas. How much time I have? Oh, I still have a lot. Just
10 minutes.
Okay, yep. Yeah. So yeah, we'll talk about the photonics, which is optical side, and talk a little bit about transparent electrode, which is optoelectronic side. So the idea was actually inspired by the plasmonic research, and we see we have absorption enhancement. And the material to boost the light absorption is actually metal. Metal is conductive. So naturally, you want to think, why don't we just make some nanowires which can be conductive, used as an electrode, and have the light absorption boost at the same time. So I was very excited, like 2-3 years ago. And so obviously, you always have a dream of one-step spray on metal contact at low temperature, which is possible, fundamentally possible with this kind of structure. So I was very excited. I'd even named the name. Why don't we call it Plus Fingers or Nano Nest or something? I was very excited. And then, obviously, 99% of the ideas, if you do literature research, someone had it already. So people have this kind of grading structures, orthogonal meshes, and they applied mainly on organic solar cells. So most of them don't have efficiency result, but some of them, yes, they have. So we think we will more focus on easy processing. So we don't want this. We don't want this. This required like a nano-lithography, very fine tool. The throughput is like you spend days in order to fabricate like a micrometer samples. We don't want that, and we want on the understand the fundamental limit of this technology. So what we do is we think we like this way, is we have a chemical synthesis of nanowires in the dispenser, and we put it on the top of the substrate, spin coating or whatever, spring on, and then we have it on top automatically. So then we did some optimization of the nanowire diameter and length and coat conditions, and on glass we actually achieved, for some part, we have better result than the widely used ideal material. So if you talk about the same resistance, it's more transparent. Or if you talk about the same transmittance, it's more conductive. So at some point. But this is very initial result, and we think, oh, what's the limit? And also the leading condition is, we also put it on solar cells, and we see efficiency enhancement, mainly due to the reduction of series resistance, as we can imagine. So when we anneal it, we actually have better connection down here, and we have sort of series resistance reduction. And when we keep on annealing it, and we see the nano wires actually broke, and we get back to normal again. It's basically not conductive in a large scale anymore. So yeah, this is the idea. Then we think about what's the limit for conductance. So we assume we have no contact resistance. We assume we have no contact resistance actually between the nanowires and between the nanowires and the silicon or whatever material. And we predict the curve, which is, this curve is an experimental curve, ideal curve, experimental curve, ideal curve. So which is very interesting. We always think we have a sort of a linear relationship between sheet resistance and surface coverage. Obviously, this is log. But for the mesh nanowire, it's not like this. And we thought, oh, what's happening there? And until one day we checked, there was like one standard physics model called percolation theory, which we can use to explain this shape of curve. Actually, you have a threshold, the surface coverage threshold. In this case, it's about 10%. When it's below 10%, it's just not conductive at all. So it's very interesting. We think we are the first person who really introduced this theory to these kind of applications, and we can explain our experimental result much better. So the black one was use a traditional theory, which assumed the sheet resistance is actually linear to the 1 over surface coverage, which is not the case. So conductance improvement. This is we did homogeneous annealing. Its performance limited and process restricted because you need relatively high temperature. But a bunch of smart guys in Stanford, they sort of use the light plasmonic effect to, if you have the light shining on the network, actually the heat will only generate at the plasmonic at the position where you have the largest resonance. So you have local heat here at the junctions, and at the surface, the interface between the substrate and the nanowires. So actually you heat melt it down, you see it melt down very nicely, but keeps the rest cool. So this is really a cool technology. I think if nanowire is gonna work one day, this is a must-have technology for that. So transmittance limit, this is some unpublished results. Disappointingly, we never find plasmonic enhancement on the nanowires. It's different from nanoparticles. So then we look into what's happening, and we find polarity. Polarization is the biggest harm. So we have very high S mode enhancement, but P mode is almost nothing. P mode means if the electric field of the light is in parallel with the nanowire. So it's basically just blocked the light. Actually, other people use this as a polarizer to block the light as you wish. So we think, no. So in the end, we get unpolarized light like this. So this one is a bare silicon. So it's always decreased because of the P mode. So we think, if we only keep the S mode and get rid of the P mode, we may have the very, very high enhancement compared with the bare silicon. So this is diameter and the surface coverage. So there was one design, use a polarization grating on top of the nanowires, and you can have the polarized light in terms of unpolarized light shining on the surface, and you may only get the star you want. So this is a very, I think you won't realize in the next 10 years, but that's if nanowire is going to work. Actually, a lot of people work on that. I doubt about that, but if it's going to work, I think this is another key factor to realize it, because you just don't need to worry about the conductivity anymore. Whatever you have it, because you always get an optical boost. So it's actually you have the light trapping effect, and you have the conductance benefit. Even if you have a benefit of a little bit on each side, and it's still quite worth doing that. So, and the last part is nano-patterning for local contacts. So we get back to the very first question is, because nanoscale is so small that it's very difficult to fabricate nanostructures in a cheap way. But in the natural, you can find the self-patterning like phenomena or method, whatever you call, everywhere. So this is a snowflake. So you just change the temperature a little bit, change the pressure a little bit, change the condition a little bit. You can have like tens of completely different shapes. That means you can actually have a lot of freedom to control the nanostructures at a microscale scale. So one of the fancy and I think promising application is we're developing AAO layer, which we find we have good passivation effect, and now we are researching on the light trapping effect. And my dream is because it's porous structure, once you can get a metal through, you can make it as a local contact as well. So another thing I want to explore is called block polymer lithography. So if you have two polymer materials combined together, and these two we generate different domains if you control nicely. In this case, it's just a proportion, and you can have polymer A and polymer B in this shape, and if you increase the composition of polymer B a little bit, you have this, C, you have this, then you have this. So if you do it properly, you can, these people have already proved that, have this kind of porous structure with a porous inside, and it's very nice film with a hole. And people demonstrate they can actually put the metal through in a hole. So that's another interesting thing to explore. Our conclusion is actually opinion sharing. First of all, I think most of the nanotechnologies that I'm talking about today will not work, unfortunately, for commercial PV products in a visible future. But when we evaluate a technology, we have to look at what's the fundamental limit. What's the limit, type of limit? Is it fundamentally limited? It's technically limited or financially limited? So if it is fundamental, just forget about it. But if it is technical or financially limited, but you see the very high potential, it's worth keeping that in mind. That's what I said. You have a to-do list. I have a dream A, B, C, D, E. Once I find a technology A, B, C, D, E could realize that, and I just click and develop a new technology. So if it is not fundamentally limited, it's probably worth putting in a to-do list and observe and see what's happening. And anyway, nano is the future if you look back into history. You always want the finer structure. for your research and for your application. And we should keep generating good ideas. That's it. Thank you.
Thank you, Zi, for giving the nice talk on the light trapping by plasmonic technique. And almost we don't have time. One or two questions. Any questions?
Yep.
That's on the optical one. You had a mini conclusion for the. Maybe you keep going back. Keep going. Keep going. So you have two graphs and one with a. I think it's higher. Can you go back? Oh yeah, I can see it. Slide 16.
Yeah.
Can you explain the top right graph again?
Yeah.
Yeah.
I try my best. So if you have a photonic crystal structure, you just consider the electron band gap thing. So it's not actually continuous. You won't have for optics, for electronics, we talk about the state of the electron can sit, and for optics you have similar thing. It's a state, not a photon can sit there. So if you have a optical band gap, this kind of structure, and you actually introduce some forbidden region and allowing region, which the photon can be or cannot be there, or what kind of momentum you should have to match that, or energy to match that. So actually give you some confinement. With that confinement, if you design a material, basically it's dielectric constant and the feature size and the shape properly, you can confine one wavelength of light and let it to propagate to the direction you want, and block the rest if you like. So you can play with the transmittance, the reflectance, and the angle you want it to go. So, but because you have to have a structure that match with the wavelengths, which more physical way is the frequency, which represents the energy of photon. So if you have the big boost of very fine control at that point, you don't have big control at other points. So this is why you see a big enhancement spike here, but you won't see elsewhere.
So what structure is it, and what is it applied on?
I think it's just amorphous silicon.
Right.
It's kind of dielectric.
Photonic crystal applied on silicon?
Yeah, if you go back to this one. Yep. It's actually this structure. No, sorry. I put the wrong plot. sorry. This is whispering gallery mode. So that corresponds to the photonic crystal, sorry.
So that graph is the same, right?
This graph corresponds to this structure. This one corresponds to that one. Okay. But it's a similar thing. You have to generate whispering gallery mode for a particular designed frequency of light. So you have the spike here. But for this structure, you may have multiple channels, but you won't have overall boost. So it's similar ideality.
Okay, any more questions?
Yep.
Okay, short question.
Maybe it's a bit more fundamental question. So how does this spherical plasmonic crystal work in a circular polarized light? Because you will have electrons generated, oscillations will happen in all the directions.
Yes.
So there must be some instances when it gets cancelled, so you have no transmission.
So this is actually what we find here. So it's actually, so what we find here with this nano wire thing is it's actually two-dimensional or one-dimensional structure, and they have the problem. So it's actually very polarization sensitive. But if you have a three-dimensional structure that's homogeneous and everywhere, you actually won't have that problem.
Yeah, but your slide number 8, it shows the oscillation of electrons.
Yes.
So that oscillations will happen in all directions homogeneously.
Yes.
Which means that some of the modes might get cancelled.
It's actually not cancelled. It's kind of superposition. So you have some kind of oscillation in this direction. If you have light in this polarization direction, you have sort of this. It's just the distribution of the electrons, or in this case, plasmons. So you distribute a little bit here, a little bit there, but it's actually the same. Because from our simulation, we simulated the same structure on the polarized light and the unpolarized light, give you the same result. Yeah.
Okay, we don't have more time. Thank you very much, Zi.
Thank you.
For giving nice talk and your answers, question and answer section. If you have more questions to discuss with him, please discuss with him later on after that seminar. I think he's sitting in the level 2, right?
Yep.
If he's sitting in level 2, you are all welcome to discuss with him to know more further about that. Okay, thank you very much. Let's give you.
Thank you.